coming from here. So this one and this one. Then I have n square by 2 minus n square plus n square. Okay, minus n square will get cancelled plus this n square. Then I have this n square by 2 remaining. Okay, this is basically n square by 2. Okay, then what I have is, yeah, so essentially these three are this thing. Then we have n by 2. This is n by 2, and then this is going to be minus n by 3. That's going to be how much? 1 by 2 minus 1 by 3 is 1 by 6, is it? Okay, that's going to be plus n upon 6. Okay, that is nothing but 1 minus 2 by 3 is 1 by 3. So we have n cubed by 3 plus n squared by 2 plus n upon 6. Okay, so that means the leading order is order n cubed by 3, which is the same as Gaussian elimination, right? In terms of the leading order, there may be some small differences in the n by 6 and so on. Okay, that is possible. Okay, but then okay, that is about the leading order for the LU decomposition. Okay, now what about the total number of multiplications or divisions involved? Total multiplications plus divisions in the forward substitution. Forward substitution. So if you look at the forward substitution, what we have is we have alpha, right? This is alpha, right? So we multiply this L with L y equals B is what we would get, right? If you have AX equal to B, we decompose A into LU. So you have LU X equals B, but UX we are calling it as Y. Then you have LY equals B is what you're going to solve. That means for LY equal to B, you have to solve for Y, right? Then you would say first one you don't have to solve. Then you have to solve for alpha 2, 1. And that means 1 multiplication, then you have 2 multiplications and so on all the way to n minus 1 multiplications, right? So that's going to give you, for forward substitution, you're going to get 1 plus 2 plus all the way to n minus 1. That's going to give you n into n minus 1 by 2 operations. Similarly, for the backward substitution, what we're going to get is backward substitution. We don't have ones along the diagonal anymore. So we have beta 1, 1 and so on. So we start with the last element. So we have to do beta and then times x equals y. So then x is going to be 1 division. Then you have 2, 3, 4 all the way to n. That means it's going to be sum to n terms, unlike sum to n minus 1 for the lower triangular matrix. So this for the forward substitution. For the backward substitution, it is 1 plus 2 plus 3 all the way to n. So this is going to be n into n plus 1 by 2. Okay, that means total here, if you were to do completely Ax equal to B, then you have earlier you have n cubed by 3 plus n squared by 2 plus n by 6 plus n by 6 coming from the LU decomposition, plus you have n into n minus 1 by 2 plus n into n plus 1 by 2. So this is going to be additional n square, right? You have n squared by 2 and n squared by 2, and then you have minus n by 2 and plus n by 2. So that means that's going to be total of n cubed by 3 plus 3 by 2 n square plus n upon 6. So that will be the total multiplications and divisions that are involved. Of course, from now on, if you're going to do the same LU decomposition for different right-hand sides, then it's going to be a multiple of so many right-hand sides that you want to do, right? But this base decomposition needs to be done only once, right? Only this will between Gaussian elimination and the LU decomposition. I think this is understood because you don't have this forward substitution step as a separate thing in Gaussian elimination, because in Gaussian elimination you do it right there on the right hand side, but here you have a forward substitution and backward substitution. So you might see some small difference there between LU decomposition and Gaussian elimination. Okay, so that is the total operation count for LU decomposition. So this is the operation count for LU for dense matrices. Okay, now it turns out to be easier this way than actually looking at the algorithm, because if you look at the algorithm, you have I less than j, I greater than or equal to j, and then for each of them you have to do the sum. So it is not very straightforward. You can give it a try if you're able to figure out from the algorithm, but it turns out to be slightly more complicated than than this way, where we would count the pure total number of multiplications and try to arrange them. Okay, fine. Any questions before we proceed?
No, sir. No.
Yeah, no, okay. So maybe you can take a look at it again, and then if you have questions, you can ask me in the next class, or if there are any mistakes or something. Okay, fine. Now let's look at solution to sparse matrix systems. Okay. Okay. Now, although till now we said A matrix could be dense, or it could be also sparse. So till now we have been looking at dense systems, which is basically we used Gaussian elimination and LU decomposition. But they can also be sparse. In fact, in many applications in mechanical engineering, either whether you do in design in the context of finite element methods, or if you do it in fluid mechanics or thermal sciences in the context of CFD, the matrix you're going to get to work with in AX equal to B it turns out to be actually a sparse matrix. Okay. Not only that, it also has another property that it is also banded. Okay. So now it is because it is sparse and banded, it is a good idea to exploit the sparsity and bandedness of the matrix. We must exploit this thing. If you do not exploit, then what happens is that we will be doing several calculations, which are actually, most of which are actually multiplications with zeros, right? Because you have written algorithm for this one, but then you realize that within A itself, several things are zeros. Okay, if several elements in A itself are zeros, then most of these will turn out to be also zeros. Okay, so as a result, we have to, because now we are looking at A, which is a sparse matrix. That means the A has more number of zeros than non-zero elements. Now, one good example for this is, and then we said this is basically a banded matrix. A banded matrix will look something like this. It will have non-zero elements only along the diagonals. That means if you take a matrix like this, it will have non-zero elements along the main diagonal, along the super diagonal, along the sub-diagonal. Only along this thing, the elements are non-zero. Okay, and if you take any other diagonals, everything else is basically going to be zeros on the top and bottom. Okay, all other elements are going to be zeros. Now, this is one particular form which is known in the literature as a tridiagonal matrix. Okay, because it has non-zero elements only along the three diagonals. Similarly, you will also have some matrices for which there are non-zero elements depending on the problem you're solving. There could be also non-zero elements along two more diagonals that are, let us say, either off or just adjacent to these three diagonals. In such case, this is known as a pentadiagonal matrix. Okay. And so on. So that is possible. And then there could be even more. It's called heptadiagonal matrix and so on. So you have basically, but then the idea is that everything between, other than these diagonals are all zeros. So, and then it turns out to be the number of zeros are much larger than whatever the non-zero elements that we have. So in such cases, we have to exploit this sparsity and the bandedness so that we can save computational time and then find an answer much more quickly. Okay. So that's what we're going to do next. Basically, we're going to look at a solution to tridiagonal matrix system. Matrix system. Okay, a matrix is said to be banded with a width of 2L if Aij is equal to 0. That means the value of the elements that the matrix contains are 0 for all I minus j modulus less than for all I minus j greater than L. Okay, so if it is going to be 0 for all I minus j greater than L, then it is going to be called as a as a banded matrix, where L is now the semi band width. Okay, this is basically half the bandwidth. So if I and if you look at I and j, and then if let us say I, if you take L equals 1, that means for any I minus j, the modulus of that, if it is greater than 1, then Aij is equal to 0. Then such a matrix is known as, for L equals 1, it is known as a tridiagonal matrix. That means only for I equal to j, or I equals j plus 1 or j minus 1, or the other way around, j equals I plus 1, it will contain non-zero elements. That means the matrix is going to look like something like, let us say, 2, 3, 4, 10, 5, 2, 2, something like this. And then there are non-zero elements only on the top and bottom. This could be 1, 2, 5, 2, and so on. And then you will have 5, 6, 2, 1, 2, something like this. And everything else is zeros. Okay. You only have non-zero elements along the three diagonals: main diagonal, super diagonal, and subdiagonal. Only that is known as a tridiagonal system. That means now in this case, obviously, it is not a good idea to decompose using a LU decomposition that we have done for the dense matrices, because most of these are zeros. We expect that a lot of alphas and betas are going to be zero. So then there is no point in applying the full matrix system. So as a result, we will look at a specific algorithm of LU decomposition that is known as LU decomposition for tridiagonal matrix. Okay. This is also known as in the literature in several names, with several names. One is a tridiagonal matrix algorithm, TDMA, and it is also known as Thomas algorithm. Okay, I think these are, you may find them in different books referring to it in a different way. But what we are going to look at is the LU decomposition for tridiagonal matrix. That is the bottom line. Now, so let me basically consider a typical tridiagonal matrix. Instead of using numbers, I'm going to again use variables, just like the way we have done. So to denote all the values in the diagonal, I'm going to use this D1, D2, D3, all the way to Dn minus 1, and then Dn. That is what my matrix is going to be. And then for all the above the diagonal, I'm going to use A1, A2, A3, all the way to An minus 1. I don't have any An because Dn is the last element along the diagonal. Okay. And then similarly, for the below diagonal, let me call it as B2, because I am starting from the second row. There is no B1, and B3 all the way to Bn minus 1, and then Bn, right? That is the 3 rows we have. This is the diagonal, this is super diagonal, this is subdiagonal, and everything else is 0. Okay. So this is a typical tridiagonal matrix that we will work with. And then we're going to develop an LU decomposition specifically tailored for this, which we can use with any tridiagonal matrix later. Okay, that means I want to now decompose this matrix into 2. So for that, I'm going to write the corresponding L and U matrices. I'm going to write the L matrix and U matrix as something like this. So my L matrix is going to be, for the previous case, we have used the Doolittle's algorithm, where we said 1 for the diagonals in the L. Let me use the Kraut's algorithm. So let me write alpha 1, 0, all the way to 0. Okay, then we have alpha 2, 0, all zeros, and so on. We have alpha n, we have alpha n minus 1, 0, and so on. And it turns out the values below this alpha in the lower triangular matrix are actually the same as what we have in the original system. That means it's going to be B2, B3, alpha 3, and so on. This is going to be Bn, this is going to be Bn minus 1. Okay, so it turns out they are all the original B's. We don't have to compute them again, so they are not unknowns. And then, so that is my lower triangular matrix. And then my upper triangular matrix is going to be 1, B2, 0, all the way to 0, and so on till my 1 here. And then 1 above this thing is going to be beta n minus 1, 1, and this is 0, this is 0, everything else is 0. Okay, equals what I have on the right hand side is basically D1, A1, 0, all the way to zeros. And then what I have is B2, D2, A2, 0, all the way to 0, and so on. We have Dn, we have an minus 1, dn minus 1, bn minus 1. This is bn, this is 0, this is 0, everything else is 0. Okay, so that is how the L and U matrices are going to look like. Okay, as you can see, just like the original matrix A, where there are several zeros other than the banded matrices, here also you're going to get all the zeros, right? So that is the design of the L and U matrices. Now it's a matter of, again, just like what we have done in the LU decomposition for the dense matrices, it's a matter of multiplying these rows with the columns and calculate what are your alphas and betas. That's all we have to do. So once you know alphas and betas, then we can calculate again using forward substitution and backward substitution, calculate what is the unknown vector x, right? So just like we have done, we have ax equals, let us say f, let me call it instead of b, because b I have already made use of here. Then once you decompose into LU x equals f, then I'm going to solve for, let's going to call ux equals y, then it's going to be solve for ly equals y using forward substitution. And we realize that now forward substitution is much easier because it has only two diagonal elements as non-zero, everything else is zeros. So once you solve for y, then you're going to solve for ux equals y, which is going to be the upper triangular matrix times x. That means solve for x. Again, we realize that upper triangular matrix only has two non-zero diagonals, then calculate what is x. Okay, that is the solution procedure that we are going to adapt. Okay, if this is the case, then let me multiply these rows with the columns and then tell you what these are. So I think I should not have written here. Okay, so what will be the, let's say if I multiply with the first row with the first column, what is that going to give me? First row with the first column is going to give me alpha 1 equals A1, right? Alpha 1 equals, alpha 1 equals D1 is going to, what's going to, yeah, alpha 1 equals D1. Okay. Then if I multiply the first row with the second column, what am I going to get? I'm going to get alpha 1 beta 1 equals A1. That means my beta 1 is going to be A1 upon alpha 1. I calculate alpha 1, use the alpha 1 to calculate beta 1, right? That's what I have done. Okay. Similarly, if I'm going to multiply the second row with the first column, that's going to give me beta B2 equals B2, right? That is straightforward. Multiply second row with the first column, that's going to give me B2 equals B2. Multiply second row with the second column, that's going to give me B2 beta 2, right? Plus alpha 2 equals D2, right? That means I can calculate my alpha 2 as D2 minus B2. Okay, so sorry, alpha beta 2 beta 1, right? So this is going to be, let me write it again. So for a second row with the second column is going to give me B2 times beta 1. B2 times beta 1 plus alpha 2 equals D2, right? Second row, second column is going to give me the diagonal element. That means I can calculate what is my beta 1 I have already calculated. So I can calculate alpha 2 equals D2 minus B2 beta 1, right? I can do that. Then I can multiply the second row with the third column. That's going to give me B2 times 0 is 0, right? B2 times 0 is 0. Then I have alpha 2 beta 2 equals A2, right? So what I have is alpha 2 beta 2 equals A2. Alpha 2 beta 2 equals A2. That means my B2 is going to be A2 upon alpha 2. Alpha 2 I have just calculated and A2 I already know. So you already start seeing a pattern here. So we'll again generalize the algorithm from the pattern that we have done before. And then let me now multiply the third row with the first column. That's going to give me 0, right? Because this is first value is 0. This is 1 here, and here everything else is 0, whereas this is non-zero, it doesn't matter. Okay, then the third row with the second column is going to give me B3 beta 1 plus alpha 3 equals, I should write more here. So this is going to be 0, B3, D3, A3, 0, right? So B3 beta 1 plus alpha 3 would be equal to B3, oh no, sorry. B3 equals B3. Multiply the third row with the third column. Third row with third column is going to give me B3 beta 2 plus, yeah, so there is a 1 below this thing, plus alpha 3 equals D3, right? So that is going to be B3 beta 2 plus alpha 3 equals D3, right? Is that correct? B3 beta 2 plus alpha 3 equals D3, okay? That's what I would get. And then similarly, again, if I do third row with the fourth column, that's going to give me alpha 3 beta 3 equals A3, okay? I'm going to get alpha 3 A3 equals, alpha 3 beta 3 equals A3, is it? Alpha 3 beta 3, yes. So alpha 3 A3. So that means my beta 3 is going to be A3 by alpha 3, okay? Fine. So we already see a pattern here. That means I can start with alpha 1 equals D1. Then my beta 1 would be equal to A1 by alpha 1. Then once I have B1, then I can calculate what is alpha 2 as D2 minus B2 beta 1. And then again, my alpha 2 as this thing and so on. That means I can generalize this thing. So if I were to generalize, okay, the algorithm, what we have is we have the first one is alpha 1 equals D1. So alpha 1 equals D1. Okay, then what I have is I have beta 1 equals A1 by alpha 1. Okay, I have beta 1 equals A1 by alpha 1. That means my beta I is always AI by alpha I, right? That's what it is. Okay. That means I can write this as beta I equals AI by alpha I. And then my, what is beta 1? Okay, beta 1 all the way to beta n, you will get this thing. Then what about alpha I? Alpha I would be, alpha 1 is already there, right? So this will go from I equals what to what? 1 to n, right? I can calculate what is my beta is like this. Then what about alphas? I can calculate alpha I equals di minus bi times beta I minus 1. Or if I would write alpha I plus 1 equals, right, I will probably use this relation, alpha I plus 1 equals di plus 1 minus bi plus 1 times beta I, where I goes from 1 all the way to n minus 1. Is that correct?
Sir, for beta I also it should be up to n minus 1.
Up to n minus 1. Okay, we don't have, yeah, up to n minus 1 only. There is no beta n, so this should be up to n minus 1. Okay, so this is up to n minus 1. Yeah, so this is up to n minus 1. Okay, so beta I equals this thing and alpha I plus 1 equals this thing. That means I have my algorithm ready. So you calculate what is alpha 1, then you calculate what is beta I and this one. That means my pseudocode could be something like alpha 1 equals T1, right? Then I would say do I equals 1 to n minus 1. My beta I equals A of I divided by alpha I. Then we have alpha I plus 1 equals D of I plus 1 minus B of I plus 1 star beta of I, right? And then and do. So once I do this thing, we're already done with calculating all alphas and betas, right? We're done with this thing, we're calculating alphas and betas. Is it clear? Okay. How many, what is the operation count for LU decomposition for this thing? Operation count for LU for tridiagonal, right? Is going to be, this is an assignment. This is one division or multiplication, and this is one multiplication. So we have 2 times n minus 1, right? 2 times n minus 1. That's all for the decomposition, which is much cheaper than earlier what we have for the order n cube by 3 plus something for the full matrix. And this is only possible because we are able to do only calculate for the non-zero elements. So this is much faster, only 2 times n minus 1, right? Then of course we have to do the forward substitution and the backward substitution. We have to do that and then calculate the operation count for that also, forward substitution and backward substitution. So we need to do that. So let me do that as well. So if I were to do forward substitution, we have alpha 1. Now I know everything here, alpha 1, B2, alpha 2, everything. So we are going to do Ly equals F. So that is going to be alpha 1, 0 all the way to 0. We have B2, alpha 2, 0 all the way to 0. 0, B3, alpha 3, 0 all the way to 0, and so on. We have alpha n, beta n. This is going to be 0, alpha n minus 1, bn minus 1. Okay, and then we have y1, y2, y3 all the way to yn minus 1, yn equals f1, f2 all the way to fn minus 1, fn. Okay, so what will be how do you calculate this one? You have alpha 1 y1 equals f1. That means y1 equals f1 by alpha 1. Alpha 1 is already calculated. Then the second one is going to be b2 y1 plus alpha 2 y2 equals f2. That means y2 is going to be f2 minus b2 times y1 divided by alpha 2, right? That's what we have. Similarly, third one is going to be b3 y2 plus alpha 3 y3 equals f3. That means my y3 is going to be f3 minus b3 y2 divided by alpha 3. Okay, now you see the pattern already. So what we can do is we can generalize this thing. So you need to calculate what is y1 equals f1 by alpha 1. That is the pseudocode. Okay, and then we have do I equals 1 to, let's say, n minus 1. Then y of I plus 1 equals f of I plus 1. Or I can even write 2 to n. That is probably easier. 2 to n. And then we're going to write y of I equals f of I minus beta of I times, beta of yi times yi minus 1 divided by alpha I. Okay, and then do. Okay, that's what we have. And then if you were to count the number of operations here, you have one division here, and you have n minus 1 into 2, right? This is going to be 2 into n minus 1. You have one division, one multiplication for each of the i's, and then it goes from n minus 1. So you see that the LU decomposition itself is actually LU decomposition is actually cheaper than the forward substitution, because the forward substitution is 2 times n minus 1 plus 1, whereas the LU decomposition itself was just 2 times n minus 1. So it is kind of embarrassingly small because we were able to take the advantage of the sparsity of the matrix. Okay, so that's why. Similarly, we can do the back substitution also. Back substitution, let me do back substitution. The back substitution is for betas, right? So the matrix we have is betas, ones and betas until n minus 1. So that's going to be like this. 1, beta 1, 0 all the way to 0. 1, it's going to be 0, 0, 1, beta 2, 0 all the way to 0, and so on. We have 1, beta n minus 1, 1, 0, 0, right? So that's what we have. And then here you get x1, x2 all the way to xn minus 1, xn equals y1, y2, y3 all the way to yn minus 1, yn. Again, if you try to identify a pattern here, you would get, you have to do the back substitution. That means xn equals yn. That's what we have. Xn equals yn. Then we have xn minus 1 plus beta n minus 1 xn equals yn minus 1. That means that's going to give you what is xn minus 1 as yn minus 1 minus beta n minus 1 xn. Okay. Similarly, I can write one above that. That's going to be n minus 2. This is 0. This is beta n minus 2. This is 1. That's going to be xn minus 2 plus beta n minus 2 xn minus 1 equals yn minus 2. n minus 2 times xn minus 1. That means my generalization for this is xn equals yn. Then do I equals n minus 1 to 1 in steps of reduction of minus 1. Calculate what is x I equals yi minus beta I star x I plus 1. Okay, and then do. Okay, now if we were to calculate the number of operations here, what we have is we have one multiplication for each of these n minus 1 steps. So basically we have n minus 1 operations, right? That means if you were to sum it together, so total multiplications plus divisions is nothing but 2 times n minus 1 for the LU decomposition plus 1 plus 2 times n minus 1 for the forward substitution, plus we have n minus 1. Okay, total that's going to be 2n plus 2n, 4n plus 1n, 5n. We have minus 1, minus 2 plus 1, that's minus 2, minus 2, minus 4. That's all. So we just have 5 and minus 4 operations for LU decomposition of a tridiagonal matrix, which is way more cheaper than n cube by 3 that we had before. Okay. So whenever it is the matrix is banded and sparse, we should always go back and use these specific tailored algorithms rather than using the general LU decomposition, because that is going to take a lot of time, especially if your n is large. Imagine if your n is, a million points or something, then this is going to only take a million order, but then that is going to take 10 to the 6 times 10 to the 6, 10 to the 12, 10 to the n cube by 3. So that's going to be a million raised to the 3, right? That is 10 to the 18, which is too large. Okay, fine. So that is what I wanted to kind of convey today. I want to quickly show. So I ended up writing a couple of MATLAB programs so that you can practice with them on your, whenever you get the MATLAB installed. So I just want to show you that. Yeah, I hope you're able to see my MATLAB session here.
Yes, sir.
Is it too small or something? Okay, I'm trying to. So this is basically. Are you familiar with MATLAB, or I'll anyway give you these codes, the sample codes, which I have. So basically, I have simple hello.m, which is basically, it says you use these CLC and clear to clear the command window and the clear all the earlier variables. Okay. Okay, and then basically input. If you input your username, it's going to display that. And there are two ways you can print that display. Either you can use display or use fprintf. Fprintf is the printf statement in Fortran. In C, you have just printf. In Fortran, it is the formatted printf. So if I were to run this thing, so I just click on run and it will say enter your name. Let's pick some name from our class. Let us say Chidambaram. Okay, so we say, oops. Pick it here, Chidambaram. Okay, it says hello Chidambaram and welcome to ME5201W Computational Methods Engineering. Okay. Similarly, I have a few other programs, which is the array operations, in which I have two arrays, array 1, array 2. I also given the names of these arrays as first, second, and so on. So first, it's going to print all the elements. Then it's going to do a vector sum. That means add each element one by one. Then it's also going to do a dot product and then display that. Okay. Of course, some of these things or many of these things are available in MATLAB itself. So, but then I want you to run these things by your own, so that when we come to code LU decomposition and other things, you can code as if it is not available, and then you can use MATLAB's version of LU decomposition to cross-check your answer. I think that is a better way. But then because we need to, let's say tomorrow you're going to implement some other algorithm which is not there in MATLAB, then we need this thing, of course. Okay. So I'm going to run this thing. So again, as you can see, it's printing element after element. It says first element is such and so on. And then eventually it will print what is the addition of the matrices, that is this one. And then the product is this much. Okay, that is the inner product. Yeah, I'm going to give you all these codes so you can learn a little bit of MATLAB with that, so that you will be able to do the assignment. Similarly, we defined in this matrix operations, I defined mat1 as These are the rows. Whenever you have semicolon, it goes to a next. And mat 3 I have given as so mat 1 and 2 I have given as 2 by 3 matrices. Mat 3 I have given as 3 by 2 because I'll be able to multiply these 3 matrices. Then I kind of get the, using the size command, I get the rows and columns into MN. Then I do, I've made some comments here, and then I basically do the sum. Sum is mat 1 ij plus mat 2 ij, and loop over ij equals 1 to m and j equals 1 to n. Similarly, I initialize the matrix multiplication, multiplied matrix as the zeros. Then I do a matrix multiplication, which has 3 for loops. Okay. And then it will display what is the mat sum, mat mul. And then I also use the built-in functions, which is the mat 1 plus 2 and mat 1 star mat 3, which are there in the MATLAB. So directly, if you use a star, it's going to do a matrix multiplication without doing all this thing. But we are not interested in that. Only for checking, we are interested in this. Okay, then I can of course run this thing. It's going to give me what is the sum, which is the 777, which is matching with this, and this is the product, that is 2014 5641, which is also matching. Okay. So anyway, I'm going to share all these programs with you. You can hopefully soon you'll be able to download and install MATLAB. Then you can run these things. I have also written the same codes in C and Fortran, but I don't think any of you will be using C and Fortran because most of you want to use MATLAB. In case if you want to use C or Fortran, let me know. I'll send it to them. I'll upload them on the course web page as well. Okay. Yeah. So with this, I'm going to stop here unless you have any questions. So this is too quick an introduction, but then when you spend some time with MATLAB with these programs, you'll be able to appreciate it better. Okay, it also shows on the right hand side, you know, what are the variables in the workspace and so on. So you can spend time and learn. If you want help, we can again take a small session on MATLAB later on if you want. Otherwise, if you're able to pick it up, then that is also fine. Questions, anybody?
Sir. Hello.
Yeah, hello. Yeah, please tell me.
Sir, can we explain why most of the mechanical applications, the matrices are tridiagonal?
So not only mechanical. So essentially what happens is that, let us say if you take a finite element or even a finite volume in CFD or something, then your elements are only connected to the neighboring elements, right? So as a result, your dependency only comes from one cell to the neighboring cells, which could be left, right, top, bottom, something like that. So it will not be connected directly to the other cells which are adjacent to the already existing cells. So as a result, you will not have any connection there. As a result, the coefficients will turn out to be 0. So you will get most of the coefficients which are for any cell, you will only see them, only neighboring to that cell. Of course, it may not be again tridiagonal when it comes to complex geometries, complex structures, unstructured meshes and all. But then there is a way you can, when you kind of reorder things, you can bring it out to be a tridiagonal matrix. If it is not possible, then still you have a sparse system, but it may not be banded. But then the sparse system, even to solve the sparse system, you should not use the LU decomposition that we have developed. You should use a slightly different LU decomposition or slightly different method in which you take advantage of the sparsity of the problem. Okay.
Okay, sir. Thank you.
Yeah, I think you'll probably, when you see examples in applied, let's say when you learn FEM or CFD, you will appreciate that most of the matrices you are getting are actually banded matrices or sparse matrices. You will not have dense matrices which are actually big for most of the cases. But then they also appear. If you use global functions and all, it will appear as dense matrices. Other questions, anybody?
Hello.
Hello, yeah.
Yes, sir. Sir, one more question. What happens when we have boundary constraints? In those times also we'll have sparse matrices.
Bounded constraints meaning, are you talking about FEM or something?
Yes, sir.
No. So bounded constraints meaning you are talking about boundary conditions, right?
Yes, sir.
Yeah. So okay, in FEM, I may not say all the time you will get banded matrices. It is possible that you will get banded matrices. You may get little denser matrices also, depending on the shape functions you would use. Okay, but then still, when you form the global matrix, you will still get a kind of a banded matrix, I suppose, which you probably have experienced. Now, these boundary conditions are actually only limited to everywhere. So we are talking about, let us say, the full matrix. Your boundary conditions might be getting affected only somewhere here or somewhere here or somewhere here. Okay, depending on the cells, but they may not be affecting the total structure as such of the entire matrix.
Understood, sir.
Yeah. When you put all the degrees of freedom, for example, this x1 could be one of the boundaries, then the coefficients for x1 will get affected. So it is possible that you may get few extra coefficients, which may not be in the same banded form. Okay, but those are they have to be dealt with separately rather than using the full LU. The full LU is only required when you have a dense matrix for A.
Sir, since we have constrained some of the sections in this case, starting from those particular rows of matrices will help in further computation in the sense of easing the computational efficiency.
Possible, but the thing is that now again you may be constraining it at several locations, so there may be several rows or columns which may be there, but I think that should not matter. You can start, I mean, ideally if you start from known values, like some kind of a Dirichlet values where you have specified the value rather than the if the constraint is in terms of the value itself, then that is the best place to start. But then these are all direct methods, so it should not affect much.
Understood.
Yeah. So are you guys able to download MATLAB or something, or install it? I don't know whether VPN connection is already given to you or not.
Yeah, we have received the email, sir, but from my side, like, where to download it.
Sure. Yeah, maybe you can soon download and then see if you are able to. So you need to be on the VPN so that it'll activate the license server when you run it. Okay. Otherwise, MATLAB will throw a license error. So please connect to VPN client to IATM using your username password, and then you should be able to install, and then license will work. Okay.
Sure, sir. Yeah, thank you for taking up with the code officer.
Yeah, no problem. In case of any issues, please let us know. We'll try to fix it. Okay.
Sure, sir. Thank you.
Yeah. So in the next class, we're going to finish up this tridiagonal thing in terms of, I'll want to make a few more comments on what instances it works and all, on what conditions it works. Then we'll look at the block tridiagonal matrices, which are a little more complicated than this. And then we'll go to something that is known as vector norms and matrix norms. Okay. So that is what is coming up in the next week lectures. Okay. Meanwhile, please practice with this one, whatever the MATLAB codes I'm going to give you. Then I'll also give you an assignment, so that once you are a little bit practice, you can start working on the assignment problems. Okay, guys, I'm going to stop here. We will catch up next week on Monday. Okay.
Thank you, sir.
Thank you, everybody. Thank you. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.